In this video, I'm going to walk you through the steps you need to follow in order to create a graph that's going to allow you to determine a reaction rate for our BglB catalyzed reaction using PNPG as a substrate. So what you can see here is that I have my data that's been collected from a 10-minute time course reaction, and I've arranged the data so that I have columns of like variables next to one another. So in the first column I have my time. Notice that the time is in increments of minutes or fractions of a minute. And then I have my absorbance values that were measured at each of those time points for my two experiments that I did with my PNPG substrate at two different concentrations of substrate, 2 millimolar and 5 millimolar. So this was one reaction that was carried out for 10 minutes, and then this is the data from the second reaction that was carried out at a higher substrate concentration, also for 10 minutes. So first thing that we need to do in order to determine that reaction rate is to graph the data with time on the x-axis and absorbance on the y-axis. Remember that by convention, when creating a graph, we're going to put our independent variable on the x-axis and our dependent variable on the y-axis. So in Excel, by default, whatever column is listed first is going to be the data that's going to go on the x, and then the other column is going to go on the y. And so if I go ahead and select these two columns of data, including the headings, and then go up to my menu at the top of the window and click on Insert, so I get to the Insert tab, and come over here to Charts, what we want to do is select a scatter graph. This is an XY scatter plot. And you can see that the data have been plotted exactly as expected, with time on the x-axis and absorbance values on the y-axis. And we can verify that that looks correct. So in order to determine a reaction rate, remember that what we're looking for is the change in absorbance, which is our y variable, over the change in time, which is our x variable. And so what we really need to know is change in y over change in x. And as we've learned previously in previous courses, that corresponds to the slope of a linear equation, or an equation that we would get from a linear regression if we were to plot a best fit trend line for this data. So we can have Excel do that for us. And what we'll want to do is click on the chart elements by clicking on this little plus sign to the right of the graph, and then come down here to trend line, where we're going to tell Excel that we wanted to add a trend line, and we're going to come over here to the drop down menu and choose more options, and over here we can select linear. This is a linear relationship that we're looking at here. And we want Excel to show us the equation of the line that it's determined, and to also show us the r² value for that line on the graph. And remember, the r² value gives us an indication of how well the best fit trend line actually represents our data. The values for r² range between 0 and 1. Close to 0 means the line does not represent the data well at all, and an r² value close to 1 means that the data are very well represented by the best fit trend line that's been drawn. And so this is what we get. So here's our equation of the line: y equals 0.0052x minus 0.0029. And so our slope term on this graph would be 0.0052. And so that would be the reaction rate that we have determined in units of absorbance units per minute. All right. Now, as described in the lab handout, what you're going to want to do after determining that reaction rate is convert those absorbance units to units of molarity of the product of the reaction, PNP, using the Beer's law equation. And we're going to go through that in class, but I just wanted to walk you through the steps for how to create this graph. Now, you can do your graphs individually, one at a time. So selecting your time data, and by holding down the control key and then clicking and dragging to select the second set of data, follow the same steps, go up here to Insert, choose XY scatter, come over here to the little plus sign, tell Excel we want it to give us a linear regression, we want it to draw us a trend line. So linear, and then we also want it to tell us the equation of the line and tell us the R squared value that corresponds to that best fit trend line. And so here we have our two data sets plotted separately on two separate graphs. Now the other thing that you can do though, if you want to put this data on the same graph so that they can be more directly compared, is you can go ahead and select the time data and both sets of absorbance values from both experiments and create your XY scatter, and that's going to plot both of your reactions and create two reaction rate curves as we can see here. Now we're going to follow exactly the same steps to add our trend lines and get our equations of the line. Only difference here is that we're going to have to tell Excel one by one which data series we want it to plot. And so here we're telling Excel to plot the trend line for the 2 millimolar substrate concentration data first. And here we have the options to display the equation on the chart and also display the R squared value. And so that's this lower concentration with the data points in blue. And then we're going to do it again, but for the other data series, 5 millimolar substrate, linear is the form of regression we want to do, show the equation of the line, display the R squared value on the chart, and now we have both of our equations. We can evaluate that R squared value and determine what level of confidence we have in the rate we're determining based on that R squared value. And then we can clean this up and create a correctly formatted figure to summarize these results so that they're a bit more clean, a bit more interpretable by the reader. And so as described in the lab handout, the conventions for a correctly formatted graph are, of course, number one, to choose the correct graph type and plot the data correctly on that graph, which we've done. So, so far so good. The second thing that we want to make sure we have is axis labels. So labels for both of our axes with units as appropriate. So we want to click this box that says axis titles, and then we can click down here in the box and put in that this is our time and the units on our time are in minutes. And then on the y-axis our label is going to be absorbance, and absorbance is unitless, so we're not going to include any units there. And then I'm going to move this legend up here. Oops. Try to do this over. So lastly, we want to make sure that we are following the convention for figures in biology. We do not use titles in biology. Instead, what we use are figure numbers and figure legends underneath the data. Now you can go ahead and add this in Excel if you want. I often will copy my figure into PowerPoint to do this, but it's perfectly possible to do this in Excel if you want to just stick with Excel. So you can enlarge your figure and then just click on the plot area. So notice I'm not clicking on any grid lines or axes or anything like that. I'm just clicking on the total plot area, and then I can grab my plot area and sort of squish it up a little bit to give me some space at the bottom of my chart. And then if I come up here to my insert menu, I can come over here to text box and add a text box underneath my graph, give my figure a number, and then provide a descriptive legend that describes the data shown in the graph so that anybody looking at the graph would be able to interpret these data on their own. And so I might say something like absorbance at 420 nanometers of a BglB catalyzed reaction with 2 millimolar and 5 millimolar P and PG. And this is going to attempt to have my text run off the side here, but what I can do is I can wrap my text, and it's going to let me do that. Wrap my text in here so it's going to stay where I want it. And let's go ahead and make sure that is concentration. And then we can add in that the 2 millimolar is in blue and the 5 millimolar is in orange. And this obviously is up to you how you want to word this, but there we go. Now we have a figure number and description of the data that we wanted to plot, and we can read our reaction rates off of those slopes and use Beer's law to convert those to molarity per minute.